in the News. Science in the News has this seminar series as part of their goal to communicate and get the general public engaged with some of the exciting research that's going on. And today we're going to hear from two very talented graduate students who are going to teach us about machine learning and robotics. So stay tuned. We'll take a break, and there are snacks and more information outside. And also make sure to stay to the end because there's a robotic gizmo to play with. Great. Thank you.
Thank you for the introduction. My name is Maria. I'm a PhD at MIT, and my work is on robotics.
Hi, I'm Ferran. I'm also a PhD student at MIT, and I do machine learning.
So today we're going to talk about machine learning and robotics. And we're going to structure the talk as first, what is a robot? And what is AI? And what has been done with them so far? But then we're going to move on. There has been a lot of progress in the last decade. So we're going to do a review on what this progress has been. And finally, we're going to comment on what is coming, what are the new areas of research that we should be looking into to make real progress and bring intelligence and robots together. So first of all, let me start with what is a robot? A robot is going to be a machine that can do actions, and the key thing is that you can do them autonomously. So that means that without any human letting the robot know what it has to do, it's already capable to move to its environment, and depending on how it looks like, it can take one or another action. When you think about robots, usually you might think robots are like in industry, like the robotic arm, or robots more like in the movies that look like humanoids. But actually, because the definition just says everything, every machine that takes autonomous actions, a drone or a self-driving car would also count as robots. But usually when we think about robots, this is the picture that comes to mind. It's an industry, it's full of robots, they are in this case just building a car, and they are doing repetitive tasks. They can do a lot of complex ones, but there's also the fact that not all of the tasks in an industry can be done by a robot. There are still going to be humans, even today. There's also another case that we can actually imagine robots not only in industries like car assembly, but also in food industry. In this case, this robot is just detecting where pancakes are, and depending on their position, it's just going to place them at the center of the line. So now we're just having robots in another different application that we might not always think about. But then, if we look at our houses, actually, how many robots do we have in our home? Probably it's between 0 and 1, and the ones that we have are just for simple tasks, like cleaning the floor. So again, we would like probably something better than this, something more smart. I would argue that maybe some of us would like to have a robot that looks like this, that just goes into our house, it's not tidy, but it looks around, it figures out what it has to do, it may see that there are some magazines, it just picks them all together, places them in the right place, and maybe figure out that the thing that it has to do is put everything into the box. So maybe after a while, figuring out what it has to do, planning, it actually makes your house much cleaner. I would argue this is the type of robots that we would like to have, but this is not real. There is a human telling the robot exactly every action it has to do. Every motion, there is a human that's saying up, down, left, right. So how do we get there? How do we get these robots? This is probably what we would like, but we are not yet there. And I think there are two main challenges to ship this kind of robotic intelligence. The first one is interaction. Robots, compared to computers, they need to interact with the world. And when they interact with the world, they are changing it. So there's some kind of communication between what the robot needs to do and how the environment is changing. And that means that the hardware, how the robot is made, is actually really important. Because just all the motors, all the machinery that is making the robot is going to interact with the world. So how do we make this better so that those interactions happen properly? There is also the question of sensors. Sensors are a part of hardware, but they have a very important tool. They give us information about the world. So the better our sensors, the better our cameras for vision, or our fingers for contact, the better we can interact and understand the world. And finally, there is control. Control to me means you're going to have some sensors and you're going to have the robot. The sensors will tell the robot what is the state of the world, how it looks like. But then the robot, given that information, will need to react, will need to interact with the world even when it knows about it. So how you do this loop is what we call control, and solving that problem is also really challenging. It has to do with interaction. But I said there were two challenges. The other one is intelligent behavior. How do we make our robots intelligent to really understand what it's everything about? And the first thing that I think is important when we think about intelligent behavior is planning. If you imagine the situation, you want to go from left to right, but the robot should figure out that in order to make the bed, it has to remove the things that are on top of it. So these actions that one goes after the other, this sequentiality, is something that you cannot hard code into a robot. It needs to learn, it needs to understand what it means, and that means planning. Another challenge that we have is human interaction. So humans do things, we know that, and predicting what a human is going to do is actually challenging. And you don't only want to predict what the human is going to do, but also how do you accumulate your behavior given that. So human interaction, how to understand this behavior is something that we need to also add into our robots. And finally, there is something very basic, but that's actually really challenging, which is language and physics. So if you give a robot an apple, it should first understand that it's an apple, and second, that if it falls, that if you throw it, it's going to fall because of gravity. So all those things that for us are very intuitive are actually hard for a robot. So now I'm going to pass it to Ferran, who's going to talk us about what about intelligence.
Cool. So in the last 10 years, we have seen a boom in artificial intelligence and machine learning. You have probably seen it displayed in the news, in the popular magazines, for example, but also in academia, we have seen an explosion in the number of research dealing with machine learning and artificial intelligence in particular. As an example, the most popular conference in machine learning used to be a bunch of nerds talking to each other about their research in a hotel, and now it's thousands of people with parties organized by big tech companies, up to the point that registration sold out in 12 minutes at one of these conferences in 2018, and people got very angry about this. And now there is a lottery just to get into the conference, which is pretty unusual for scientific conferences. Okay, so what is all AI and machine learning about? So we have AI and artificial intelligence, which is basically giving computers the ability to display intelligent behavior. What is an example of intelligent behavior, for example, is helping us get here from MIT. So we used kind of Google Maps just to tell us the route to get from MIT to here in an efficient manner. Or, for example, in 1997, there was a computer that beat Garry Kasparov, at that time the world champion at chess, at this game. Similarly, there is machine learning, which is a subfield of AI. The idea is that in these two cases, a human program or a team of humans program every line of code of this artificial intelligence in order for it to display this behavior. However, machine learning says, okay, maybe programming every line of code is not only tedious, but sometimes very hard. Can we get help from data that will tell us actually how to display this intelligent behavior? Let's say, for example, we want to classify an email as either spam or a good email that we actually want to read. One thing we could do is say, okay, many humans have classified emails as spam or not spam before, so let us look at the words of those emails. So, for example, emails containing spam may contain the word Bitcoin or win money or buy something. And so it's likely that if some email contains these words, it's likely spam. In contrast, maybe something that contains the word meet tomorrow or lunch, maybe it's likely not spam. And so now when we receive a new email that we have never seen before, we can kind of exploit this knowledge to now classify it without even knowing what the human would think about. A subfield of machine learning that has gained a lot of popularity recently is deep learning, or also neural networks. And it's essentially a set of units and connections. We'll talk more about this later. But basically, you should think about them as something that allows us to do very smart applications in the last few years. We'll talk more about this later. Let's first talk about machine learning, because it's basically the workhorse that has enabled most of the progress in AI in this last few years. As we said, it's a subfield of AI that exploits data in order to generate intelligent behavior. There are three types of machine learning. The first one is supervised learning. Imagine we want to teach a machine to differentiate between cats and dogs. And so one thing we could do is give it labels, images of cats, and say, okay, this is a cat, this is a cat, this is a dog. Maybe as humans, with a few examples, we already know that we have enough to learn to differentiate cats and dogs. But
maybe a machine usually needs more like a few thousands of words, of examples, sorry. Another example is unsupervised learning. In this case, we don't have pairs of data. What we actually have is the data itself. And what we have to find is the structure of this data. So this is an example from our own research for a couple of years ago. And imagine you have the TV series House, which consists of a medical doctor who is the protagonist, and then there's a few other doctors that are also in the main cast. If you look at all the pictures that appear in the TV series across all the episodes, and you can see that there's a big cluster here that is a lot of faces that are very similar to each other. And it's from these, the densest region actually corresponds to the main character. Even though no one told us who the main character was, the machine can interpret it as such. Then regions that are dense but less dense, like this one here, belong to someone in the main cast, and then sparser regions where there's a very few points, maybe it's only a character that appears in one episode and nothing else, or some other images that were actually not faces and were misclassified as faces. Finally, imagine we want to teach a machine how to act. So for example, the closest thing that we have to this is teaching an animal how to act. We don't know, for example, imagine we want to teach a dog how to sit properly or jump properly. We cannot teach a dog move this muscle in exactly this way. The only thing we know how to do is reward good behavior. We know how sitting looks like, and we know how jumping looks like. So if the dog jumps and we like the jump, we'll give it a cookie. And the dog will keep doing whatever finishes by us giving it a cookie. In the same way, we can have robots that try to be cookie maximizers and try to find the actions that lead to the best reward. Okay, now we have seen 3 possible types of machine learning. How would we go on and build such a system? Let's say, for example, let's start, in this case, by supervised learning, which is the most common example. And let's say we wanted to classify whether this image is from a cat or from a dog. And let's say, okay, what if we had to design and kind of hard code the results of this machine learning? First, we have to notice that this image, even though we see it as kind of a cat, the machine learning algorithm sees it as a bunch of numbers, as a bunch of pixel values. So it's pretty hard to start from there. Maybe one thing we can say is, oh, maybe if we had the edges of the image instead of the raw pixel values, it would be easier to classify it as a dog, as a cat, sorry. So maybe if we had these edges, it would be better. Okay, how would we build such a detector? Let's take, for example, a simpler example where we have a kind of the sky and the sea, and we'd like to just detect the edge between both. We can see there's kind of 2 rows where there is one row that's very dark and one row that's very light. And if we find these consecutive rows, we'd have essentially found the edge between both. Maybe in contrast, such a row would not exist here because every row has kind of the same pattern of whiteness or blackness at every row. It's basically the same. So this horizontal edge detector would like to kind of say, oh, I want you to sum the brightness of one row and subtract the brightness of the row above. And in this way, we'd have a horizontal edge detector that if we apply it to the cat picture, you can see it takes mostly the horizontal stripes. Similarly, we can do the opposite for vertical, and in this case, what we do is compare 2 consecutive columns and say, okay, if there is a big difference, that means there is likely a vertical edge. It doesn't need to be just black and white or even vertical and horizontal. We can have also colored detectors or even diagonal detectors. Okay, but it was us humans that designed these detectors. Can we do better and let the machine figure out these detectors? And that's where neural networks come in. So first, the way you should think about the neural network is a generic way of learning this type of detectors given enough data and enough compute. If you give me thousands of data points and kind of a big computer, I will be able to learn this, but if you give me maybe only 10 data points, maybe a neural network is not the best way to go about it. There are other methods in machine learning to do so. Also, they're very loosely inspired in the brain, emphasis on very loosely. The idea is that there is kind of a few units and connections, and this is analogous to neurons connected to each other in the brain. And the final way that you should think about neural networks is kind of an automatic way of designing the features we were talking about. So as an example, here are some of the features that the neural network learned as compared to the one we designed in the slide before. Good. So how do we do it? At first, we haven't seen any data. So the detectors that we were talking about before will start at random. So we had some numbers and they will start at random. That's the best we can do. However, if we use these detectors it's likely we will make mistakes. So for example, we may classify this cat as actually only being a 30% chance of this being a cat and 70% of this being a dog. Maybe we can learn and optimize these numbers in order for us to minimize this error. And in this way, we'll be able to find the optimal values of these numbers for us to now classify this as a cat with confidence. However, one of the other things that neural networks have is that we are now stacking them into many layers. That's why we call it deep learning. The idea is that we have the input, in this case the cat, and we have seen how we can build a layer of detectors. But having the edges may not be enough to detect it as a cat. So one thing we can do is, okay, here we have some kind of representation that we're learning at this level, kind of very low-level textures. Can we exploit this to build even more complex detectors? And so if we do the same, but now taking the output of this as the input, we can see that we can represent more complex textures, and we can go up and up. So for example, we can start to detect things like objects, or even kind of wheels, or dogs, or houses, and then it gets more abstract. And the network learns very complex, abstract representations until being able to actually predict this as a cat. Notice that first, there is a lot of layers, and two, there is some numbers everywhere, because every layer has all these filters with numbers that we need to learn. So this takes a lot of compute to be able to evaluate, and also we need a lot of examples in order to figure out all these numbers that are in these boxes here. So for neural networks to be able to succeed, we needed two breakthroughs. The first one was a breakthrough in terms of computing, and it was the realization that the type of compute that we have in gaming industry, where we have to render things, and this is usually done in parallel, can also be used for AI research. And so we have this type of computation that is used in both. But now there is kind of people researching ways to target, in particular, the type of computation we have in AI. And then there's kind of this internet scale data. We have tons of data now. The reason is that first, maybe we have teams of humans that crowdsource and generate this data, but more importantly, we have companies that are generating tons of data. As an example, when you get into Netflix for the first time, someone Netflix asks you, give me 3 movies that you like. The reason Netflix asks you that is because then it will recommend movies that people that also click these 3 movies also liked. And in this way, they can build a recommendation engine. Similarly, when you go to Google and mistype something, and sometimes it suggests something pretty smart, so here I mistype Barack Obama, it leverages that people sometimes made the same misspelling as you, and then afterwards correctly type Barack Obama, and then it suggests what they did. And finally, Uber makes tons of rides every night. And so it can see patterns in where people ask to get a ride and where do they want to go, and in this way they can predict what will happen next night and direct riders to some locations even before they actually get the rides. Here we'll finish this first section of the talk, and we're ready to take your questions. Thank you.
Computing power, that has been a challenge for this. What do you guys see in the future of helping with the computing power?
Yeah, so maybe the closest thing that to this computing power to solve this is that people, now there's startups building specific hardware to be able to run these neural networks. So at the beginning, AI researchers kind of picked these GPUs, they're called, for gaming, and kind of said, okay, what can we do with them? So they were pretty good, better than the generic compute, but they were still not perfect. So now, given the demand for AI, because there's lots of services like Netflix or Google that are using it, there's some people that said, okay, can we build specific computers that run this very, very effectively, only this type of AI and nothing else? And so that's probably the biggest trend. The other trend is that there is these clusters of computers that you can run them in parallel and then connect computers together, and in this way, that's another way you could scale this up. Should we just move on, or?
If there are no other questions.
Okay, cool. 1 second. Okay,